In this section of the lab, we're going to explore limits of functions of several variables. And for the purposes of our discussion, we're going to restrict ourselves to functions of two variables, like f of x, y. Now, the reason why limits in this realm are a little bit more challenging is that we can approach a point from essentially infinitely many directions. And in order for the limit to exist, we need that limiting value to be the same no matter how we approach a particular point AB. Okay, so that's a little bit different than what happens in Calc 1, where we just approach from the right and the left. Now we've got many different paths, and that's emphasized right here. So graphing utility can be really helpful for looking at these functions. It's not the end-all be-all because there's a special note here. Graphing software, they usually produce an image by connecting the dots. And so if you have a hole in your graph or discontinuity somewhere, sometimes the software will just drive right through that hole and it will look like a nice continuous curve when in fact you've got holes in there. So you do need to be very careful with your analysis. All right, let's get started with some examples. The first one here, we want to look at the function f of xy equals xy over x squared plus y squared plus 1. So let's do a 3D plot. This looks beautiful. We have a nice smooth curve. We could walk or skate or bike across the surface without too much difficulty. Okay, it certainly looks continuous. And in fact, we see that f of xy is defined for all real values xy. Now, let's change the function slightly. I'm going to remove that plus 1 in the denominator and now look at what happens to the plot. So if we were coming along this ridge, it looks like the z value is approaching maybe a 0.5. On the other hand, if we were walking along this valley down here, it looks like the z value is approaching perhaps a negative 0.5. And there's some concern about, first of all, is the function continuous at the origin? And certainly it's not. 0, 0, it's not even defined at that point, so certainly it's not continuous there. It doesn't look continuous. But even though the value is not defined, does the limit exist? Well, intuitively, if we come along this ridge, we get one value. Come along the valley, we get a different value. So the limit does not exist. Right? To be a limit that exists, we have to get the same value independent of the path we take. Okay. Let's take a look at this next function. So now we've changed a few things. We've got an x squared y in the numerator. The denominator has an x to the fourth plus y squared. So let's shift enter. Take a look at this plot. This is very bizarre. Beautiful. It's also a very beautiful sort of plot. We would have a lot of trouble walking around or skateboarding or biking through that surface. At least I would. Maybe you wouldn't, but this is a very difficult surface to navigate. And we can ask ourselves the same sorts of questions. Is it continuous at the origin? Well, no, it's not continuous because this is not even defined at 0, 0, right? So it's definitely not continuous, but then we would still want to ask, well, does the limit exist? Well, let's see, as we come along this kind of parabolic path up on the top here, it looks like we're up on a ridge, and it looks like that value is around 0.5. On the other hand, if we're walking along this valley down here, and that also kind of looks like some sort of parabola, maybe we can flip it over and take a look at it. It does kind of look like a parabola, that looks like we get a different value. So again, it looks like the limit as x, y approaches 0, 0 does not exist. All right, let's take a look at the contour plot here. Very interesting contour plot. And there's a little bit of a note down here. So notice that the parabolic level curves all approaching the same point, the origin. This means that f has different constant values along paths that approach the same point. So f has different limiting values along these paths. So that's a very interesting observation you can make from the contour plot. Okay, let's take a look at the following. So suppose we had a function x plus y over x minus y. Let's hit Shift Enter here. And notice that we're getting an error message. And so Mathematica is certainly not happy about trying to plot this surface. Okay, let's take a look at this one. On the other hand, this looks quite lovely. It looks smooth. We know it's there's a hole in there, right? Because when x and y are both 0, this function is not defined. So that's kind of interesting. Here's another interesting plot. Pretty cool. So, as you look at these functions, you want to ask yourself, does the limit exist? Is the function continuous? What can we learn from this visualization? All right. Now, in this example, this is a pretty challenging example, and so I want to give you a few ideas for exploring this example. I won't give you the answer, of course, but here are some things you can do to explore. So the first thing here is I'm going to create a Mathematica input cell. And the first thing we want to do is we want to look at the function. Okay, so we want to do a plot 3D. And you can get to the plot 3D either by copy pasting code or go to Classroom Assistant Palette. Make sure this is on my screen. Over on the right hand side in the basic commands area, click on 3D, and then you can do a plot 3D. Okay, and you can type in the function as well as your min and max values for x and min and max values for y. Okay, so let's do that here. And I'm going to do x from -10 to 10 and y from -10 to 10. Okay, I can't really tell what's happening at the origin, so let's just make this a little bit more sensitive to what's happening at the origin. So I'm going to change my viewing window from -2 to 2 in both the x and the y. Okay, and we're starting to see things a little bit more clearly here. Okay, that's good. Now, and I just want to make sure we've got that multiplication there. Good. Now, the next thing we want to do is we want to look at what are all the possible limiting values? Like, what are all the possible limits that you could get for straight line approaches? So they want us to substitute y equals mx in the limit. Okay, so let's take a look at a few of these. So first of all, let me label this. I'm going to create a text area. Let's let m equals 1, and we'll substitute y equals 1x, that's like y equals mx, into the function. What is the limiting value? Okay, so here's what I want to do. My original function looked like x times y, but I'm going to make the substitution that y equals x. Okay, so this is going to be an x. Down here, instead of y squared, this is just going to be an x squared. Okay, and now the question is, what is the limit? What is the limit of that function? So let's go to our Classroom Assistant palette again. On the Classroom Assistant palette, you can click on the Calculus tab and click on Limit. So let's put our expression in there. The variable will be x, goes to 0. Okay, it looks like 1/2. So if we were to come in here along the path y equals x, and it looks like it's right on this ridge, the z value should be getting close to 1/2, and that certainly does look like it's the case from our plot. Okay, let's do this again. So let's create a text, and now I want to let m equal 2. So I'm going to substitute y equals 2x into the function. What's the limiting value? Okay, so instead of y times x, this is going to be y times a 2x. Instead of y squared, it's going to be a 2x all squared. Okay, and that's a 2/5. And you could keep going, trying y equals mx for different values of m. And you should do this. Explore the function. Explore the limit.